Hello and greetings. This is Dr. VC Sontake and I am going to take the course Heat Transfer. Objectives of this video lecture to derive the expression of LMTD, that is log mean temperature difference for parallel flow heat exchanger. Log mean temperature difference for parallel flow heat exchanger. In any heat exchanger, the temperature difference between the hot and cold fluids varies from point to point as the fluids move from inlet to the outlet of the heat exchanger. Also, it is observed that the temperature variation between hot and cold fluid is not linear. Rather, it varies from point to point and follows some mathematical law. In addition to this, various modes of heat transfer are involved, like conduction and convection. Therefore, based on the concept of appropriate mean temperature difference, also called as the log mean temperature difference, the total heat transfer rate in the heat exchanger or by the heat exchanger between hot and cold fluid is expressed as capital Q is equal to U into A into delta Tm, where delta Tm is called log mean temperature difference, or in short it is called as LMTD. In the above expression, U is overall heat transfer coefficient and A is total surface area of the heat exchanger available for heat transfer. Expression for log mean temperature difference for parallel flow heat exchanger can be established by making following assumptions. Assumption number 1 is one-dimensional steady state flow. During heat transfer between hot and cold fluid, the steady state is assumed, and it is also assumed that flow is steady flow. That means during steady state, the heat transfer rate remains constant and the mass flow rate of both the fluids also remain constant. 2. The overall heat transfer coefficient capital U is constant throughout the heat exchanger. 3. The heat capacities of the fluids are constant through the heat exchanger. 4. The heat exchanger is perfectly insulated, which ensures no heat loss to the surroundings. The outer surface of heat exchanger is assumed to be perfectly insulated so that heat transfer is ensured to taking place between hot and cold fluids only. No heat transfer or heat loss must be taken from the outer surface of the heat exchanger. The changes in kinetic and potential energies of the fluids are negligible. It is possible that there is an elevation difference between inlet and outlet of the heat exchanger with reference to some datum point, and hence it is quite possible the kinetic energies and potential energies of hot and cold fluid may vary. However, this variation we are neglecting during derivation of LMTD expression for parallel flow heat exchanger. 6. Axial conduction along the tube is negligible. So whatever heat transfer takes place, whatever heat transfer takes place between hot and cold fluid, that takes place only in the radial direction. There is no partial phase change in the system. There is only temperature change in the hot and cold fluid. 8. The temperature at any cross section of the stream of hot or cold fluid is uniform. That is at any cross section of the heat exchanger. Figure 1 shows the fluid's flow direction and temperature variation of hot and cold fluids flowing through the parallel flow heat exchanger. Let us consider a heat exchanger in which the outer surface of the heat exchanger is assumed to be perfectly insulated. Two fluid streams in the form of hot and cold fluids are flowing. For the sake of assumption, we are considering left hand side of the heat exchanger as inlet and right hand side of the heat exchanger as outlet. The hot fluid is flowing in the upper direction with the mass flow rate m dot h, specific heat Cph, and inlet temperature Th. The cold fluid is flowing with the mass flow rate m dot c, specific heat Cpc, and inlet temperature capital Tc. Let us consider an elementary area dA of this heat exchanger through which the heat is being transferred from hot to cold fluid. And as a result of this heat exchange, the temperature of hot fluid changes from Th to Th plus Dh, and temperature of cold fluid changes from Tc to Tc plus Dc, where Dh is decrease in the temperature of hot fluid, in small decrease in the temperature of hot fluid, and Dc is the small increment in the temperature of cold fluid as a result of a small amount of heat transfer dq through the small elemental area dA of the heat exchanger. The diagram below the schematic shows the temperature variation between hot and cold fluid in the heat exchanger. On the y-axis, we are considering area or length of the heat exchanger. The most extreme side of the graph represents inlet of the heat exchanger, where length or area is 0, and the right hand side represents outlet of the heat exchanger, where area is entire surface area. So as a result of heat transfer between hot and cold fluid, temperature of hot fluid will be changing or decreasing from Thi to Tho, and temperature of the cold fluid is increasing from Tci to Tco. There will be change in the temperature of hot fluid dTh, that will be quite infinitesimal, and there will be increase in the temperature of cold fluid dTc. Delta Ti represents temperature difference between hot and cold fluid at the inlet. In case of parallel flow, it will be Thi minus Tci, and delta To represents temperature difference between hot and cold fluid at the outlet of the heat exchanger, that is Tho minus Tco. In this representation, I represents inlet, O represents outlet, suffix H represents hot fluid, and suffix C represents cold fluid. So m dot is the mass flow rate of the fluid in heat exchanger in kg per second. Small c suffix p represent specific heat of fluid at constant pressure in joule per kg Kelvin. Capital T represents temperature of the fluid in degree Celsius or Kelvin. Suffix I represents inlet condition of heat exchanger. O represents outlet condition of heat exchanger. Small h represents hot fluid, and suffix C represents cold fluid. So with this nomenclature, let us move on. We will be referring this diagram. Let us consider an elementary area dA of the heat exchanger. The heat flow rate through this elementary area is given by dq is equal to U into dA into delta T, which can also be given as U into dA into Th minus Tc. Let us say this is equation number 1. In this elementary area of the heat exchanger, this elementary area is very small. Heat transfer, in fact, a small amount of heat transfer dq is taking place from hot to cold fluid. So this expression for dq is given in the form of equation 1. Due to heat transfer dq through this small area dA, hot fluid is cooled down by amount dTh by giving away its heat to the cold fluid, and cold fluid is heated up by taking heat to the amount dTc. Hence, if I apply energy balance over this elementary area dA of the heat exchanger, it can be given as dq is equal to minus m dot h cph dth is equal to m dot c cpc dtc. It can also be written as u into dA into delta t. Let us say this is equation number 2. So under steady state condition, the rate of heat exchanger will be equal to rate of heat transfer by hot fluid is equal to rate of heat taken by cold fluid. In this equation number 2, dTh is negative because temperature of the hot fluid is decreasing, and dTc is positive because temperature of the cold fluid is increasing. From equation 2, I can rearrange the equation 2 for this dTh and dTc. So dTh is equal to minus dq over m dot h cph is equal to minus dq over cph, capital C suffix ph, where capital Cph is equal to m dot h into cph, and it is heat capacity rate of hot fluid. In the similar fashion, dTc is equal to dq over m dot c small cpc is equal to dq over capital Cpc, where capital Cpc is equal to m dot c into cpc, and this is heat capacity rate of cold fluid. Now let us take the difference of these two temperature differences. dTh minus dTc can be written as equal to minus dq over capital Cph minus dq over capital Cpc, or this implies d into Th minus Tc is equal to, taking dq out of this, minus dq in bracket 1 over Cph plus 1 over Cpc. Let us say this is equation number 3. Now we have equation number 1 like this: dq is equal to u into dA into delta t is equal to u into dA into Th minus Tc. From this equation 1, let us put the expression for dq into the equation number 3. So it will give, equation 3 will convert in this form: d into Th minus Tc is equal to, putting the value of dq, minus u into dA into Th minus Tc into 1 upon capital Cph plus 1 upon Cpc. Now rearrangement of this equation will give the equation in this form: d into Th minus Tc over Th minus Tc is equal to minus u into dA into 1 over capital Cph plus 1 over Cpc. Let us say this is equation number 4. Now integrating the above equation from inlet area Ai to the outlet area A, that is from the inlet to the outlet section of the heat exchanger. So integrating the equation number 4 from inlet I to the outlet O of the heat exchanger. On the left hand side, I can write it as integration of I to O dTh minus d into Th minus Tc over Th minus Tc is equal to this term 1 upon Cph plus 1 upon Cpc is constant because a specific heat of hot and cold fluids during the heat exchange in the heat exchanger we have assumed constant. So the entire term I can take out from the integration sign. So in the integration sign it will remain U into dA from inlet area I, inlet area A equal to 0 to outlet area A. Now here let us talk about the boundary conditions, how boundary conditions are varying in the heat exchanger in the left hand side of the expression and in the right hand side of the expression. In the left hand side of the heat exchanger, we are going to consider boundary conditions in the form of temperature, that is at inlet and outlet how the temperatures of the fluids are varying, and in the right hand side of the expression we are going to consider the boundary condition in the form of area of the heat exchanger at the inlet and outlet. Obviously at the inlet the heat exchanger area will be 0 and at the outlet heat exchanger area will be maximum, that is equal to A. Now after integrating and putting the boundary condition, I will get the expression as log of THO minus TCO over THI minus TCI is equal to minus UA into 1 over CPH plus 1 over CPC. So how this will come? So in the left hand side, that is at the inlet, temperature of the heat exchanger, temperature of the hot and cold fluid in the heat exchanger are THI and TCI, and at the outlet the temperature of the hot and cold fluids are THO and TCO. So that is why these temperatures are written. Similarly, in terms of area, the heat exchanger area is 0 and at the outlet the heat exchanger area is A. So after putting these boundary conditions in the left hand side and right hand side of the expression, I will be getting this expression. So let us say this is equation number 5. Now the total heat transfer rate between the two fluids is also given by energy balance and can be written as in this form, and this equation comes from this very fact, that is rate of heat transfer in a heat exchanger is equal to rate of heat transfer from the hot fluid is equal to rate of heat transfer to the cold fluid. Expanding this equation will give the rate of heat as Q is equal to CPH, capital CPH into THI minus THO is equal to capital CPC into TCO minus TCI. Let us say this is equation number 6. Now rearranging this equation number 6 in the form of expression for 1 upon CPH and 1 upon CPC. So it will give the expression like this: 1 over CPH is equal to THI minus THO over Q. Let's say this is equation number 7. And 1 over CPC is equal to TCO minus TCI over Q. Let us say this is equation number 8. Now putting the values of 1 upon CPH and 1 over CPC from equation number 7 and 8 into equation 5, and we get the equation as log of THO minus TCO over THI minus TCI is equal to minus UA into THI minus THO over Q plus TCO minus TCI over Q. I can further rearrange this. Log of THO minus TCO over THI minus TCI is equal to, taking Q out of the bracket, will give minus U into A over Q into TCO minus THO plus THI minus TCI. Rearranging this temperature difference in terms of temperature difference at the outlet of the heat exchanger and at the inlet of the heat exchanger. Further simplification will give log of THO minus TCO over THI minus TCI is equal to, taking the minus sign inside the bracket, will give U into A over Q inside the bracket THO minus TCO minus THI minus TCI. Hence, the total heat transfer rate Q will be U into A THO minus TCO minus THI minus TCI over log of THO minus TCO over THI minus TCI. If I compare this equation with the Q is equal to UA into delta Tm, I will get delta Tm, that is log mean temperature difference for parallel flow heat exchanger. Let us compare these two expressions. So comparison of these two equations will give me expression for LMTD for parallel flow delta Tm is equal to THO minus TCO minus THI minus TCI over log of THO minus TCO over THI minus TCI. So this is the expression for LMTD for parallel flow heat exchanger. I can also write this expression like this: delta Tm is equal to delta To minus delta Ti over log of delta To over delta Ti is equal to, rearrangement of this will give me delta Ti minus delta To over log of delta Ti over delta To. This is the most generalized way to represent the expression for LMTD for parallel flow heat exchanger. In this expression, delta Ti is the temperature difference between the hot and cold fluids at the inlet of heat exchanger, that is Ai is equal to 0. So delta Ti is equal to Thi minus Tci. Both the fluids are entering at the inlet of the heat exchanger in case of parallel flow heat exchanger, and delta To represents the temperature difference between the hot and cold fluids at the outlet of the heat exchanger, that is AO is equal to A. So delta To will be THO minus TCO. Both the fluids are leaving at the outlet of the heat exchanger. So this way we could derive the expression for LMTD for parallel flow heat exchanger. Learning outcomes of this video: after watching the video, learner will be able to derive the expression of LMTD for parallel flow heat exchanger. So with this, I come to an end of this video lecture. Thank you for your kind attention and passionate listening. Happy learning.